Why do we do all of the things we've just been doing? And here is the reason why. Here is where this is most useful. So let's go ahead and try solving this first. So find out solution. Okay, we got a couple different avenues. For one though, I like seeing the difference of two cubes of x and 2. So x and 2, x squared, multiply, square the 2, and then match, opposite, plus. So x equal to 2 here, here. Can't factor, use a quadratic formula. We end up with, and I'll let you go ahead and do that, 1 plus or minus I squared to 3. After you simplify and everything. Okay? Let's just, for our own curiosity, go ahead and graph these on the complex plane. 2, 2, 2. So 2, 0, 2 is right here. Negative 1 square root of 3 is somewhere about here. Negative 1 negative square root of 3 is about there. Interesting. Oh, I know. While we're here, let's put these in the complex form. So here that's going to be 2, don't know why I put the 2 cosine 0 plus I sine 0. This here, the radius is 2. How do I know that? Again, so when I'm looking at this, I recognize the 30, 60, 90 right there. How do I know that? Leg, other leg. Long leg is square root of 3 times the short leg. So the hypotenuse, the r, is that. And so this is, oh, pi over 3. So that's 2 pi over 3 plus I sine of 2 pi over 3. Down here, same radius, same legs, but the minus directions. And being quadrant 3, it's 4 pi over 3. It was the 4 I was talking about. Okay. So now, well, pretty. Now you might say, wait a minute. What if we would have just solved for the way we can, and then take the cube root? What happens there? Well, the cube root of 8, we know that is 2. Well, this version only gets you real values. We wanted all values. Okay, that's why we needed to be able to do this. Now, what happens if we have roots, zeros of something, where we can't get to a quadratic? We can't see it. We don't find it. What happens? Well, this is where our trig formula, our trig form of the complex numbers, we're able to do it. Now, granted, remember, all numbers, even reals, are complex. They just would have, pure real numbers have no I, 0 I. Okay, so for the, let's decipher this kind of formula here. Okay, cube and r to the n, well, it looks like just what we've done before. When we multiply, divide, power, root, we root. 0 plus 360k over, yeah. Well, this k, first of all, is a counter. We start counting at 0, and then we start counting up 1, 2, 3, 4, 5, bop, all the way until we get 1 less than the actual root. Okay. I know that looks strange. How do we do this? Well, this is really like the 0. What's our first one with no movement, then second, third, fourth. We'll take a look at that a little bit more detail too. So, example 2 here. Well, that's just 8. So let's find these roots using this formula, and we should get what we got with the sum, or the difference of two cubes, because we're taking the cube root of the same number. So cube root of 8 that's the new r. Now for the three different thetas. Well, start counting at 0, 1, 2. Notice how many do we have? Because if you start counting at 0, you'll always end up with one less than we start. Now we just plug it in. So the original 0 plus 2 pi times the k over 3. The index. And that's 0. 0 plus 2 pi times 1 over 3. 2 pi plus 0 divided by 3. Now plug in 2 for k. Alrighty. And then what are those three numbers? 2 cosine 0 plus I sine 0. 2 cosine 2 pi over 3 plus I sine of 2 pi over 3. 2 cosine of 4 pi over 3 plus I sine of 4 pi over 3. Did we get those before? Yes, we did. 0. 2 at the angle at 0, 2 at the angle of 2 pi over 3, 2 at the angle of 4 pi over 3. Ta-da! Again, this is working when we have ways for cube roots because we can get the real and use the quadratic formula. I don't know how to do that in example 3. We don't have a fifth root. One of those gonna be real. Or yeah, maybe not, because we start with a non-real number. This is complex to start with, kind of thing. So let's walk through it. Fifth roots. So our n is 5. So our new r is the fifth root of 32, and I picked it to be nice. Now for the 5 different angles, 5 different thetas. Start counting at 0 until you get a total of 5 options. Oops, I did that. I knew I would. So 0, 1, 2, 3, 4 gives us 5 options. Plug it in. So 3 pi over 4 plus 2 pi times 0 over 5. So 3 pi over 4 divided by 5 times a fifth. So let's do that with 3 pi over 4 plus 2 pi times 1 all over 5. Now, hesitating, that's okay. So over here, 2 pi. So we got 11 over 4 divided by a fifth, or times a fifth, or divided by 5. 11 over 20 pi. So 3 pi over 4 original plus 2 pi times 2 over 5. So that's 4 pi. Well, 4 times 4 is, so this is now 16 plus 3 over 4 times 5. Do the same thing with the 3 then. So 6 pi, which is 24 over 4. Now, if you're starting to see a pattern, excellent. It's okay if you don't. Because it's just, we could go ahead and do this. This is the one time where sometimes degrees works better because of the So 8 over 4, which is really 32, sorry, 8 is 32 over 4. 32 plus 3 over 4 times 5. Wait, I could reduce that. We could reduce that to take out a 5. 7 pi over 4. And so now we have 5 different numbers to write. So 2 cosine 3 pi over 20 plus I sine 2 cosine 11 pi over 20 plus I sine 11 pi over 20 cosine 11 pi over 20. Oops, not 11, we're at 19 now. 19 pi over 20 to cosine 27 pi over 20. And then this here. Now, no, you can't, there is no, oh, could we just not write them down? You have to write them down. Have to write down the final answers. So, again, take a look. There may be a pattern between 3, 11, 19, 27, 35. See if you can catch that. We'll take a look at some of that, and we'll take a look at, this is a lot of writing. That's why we don't do much beyond 5th, especially for assessments. But there's a short form for this, which we'll look in Part B.